We're going to take a look at the answers to the concept questions for the kinematics section. The first question asked, okay, if an object is moving but slowing down, what do we know about the acceleration and the velocity of those two objects? We know that they're going to be in the opposite direction. I've used this example in class before, that if someone is running in one particular direction, but they're slowing down, you have to push them in the opposite direction to make that happen. The same thing holds true if we throw something up into the air. If I throw it up into the air, the velocity is up, but the acceleration is down because that's the way the gravity goes. And obviously we know that when we throw something up in the air, it's got to be slowing down, because if it went at a constant speed, it would keep going forever and it would never come back. If it got faster, it would really continue going and never come back. So when they are in opposite directions, throwing it upward but gravity is down, we know that the acceleration and velocity being in opposite directions means slowing down the object. Conversely, if an object is getting faster and faster, we know that we have to be pushing, or it has to be pushed in the same direction, making the acceleration and velocity both going in the same direction. So the picture on the screen, you can see that if somebody's running to the right, if you want to make them go faster, you have to push them to the right, putting the acceleration and velocity in the same direction. That again holds true if we were thinking about throwing something up in the air again, that if I throw it up in the air, it's slower, slower, slower on the way up, but on the way back down, the velocity is down, gravity is down, which is accelerating it down. So when the velocity and acceleration are in the same direction, that's when things are getting faster and faster and faster all the way down. Now, if I have two objects and one is heavy and one is not heavy, like you can see in this GIF, it's a bowling ball and some feathers, which one's going to hit the ground first if I drop them at the same time? Well, the answer is they're going to get to the ground at the same time. We did a lab like this in class where you dropped a big heavy steel ball and we dropped a much lighter marble and we let them go, and they should have hit the ground at the same time. That worked when we did it in class with a feather and a steel ball. We just had to put them on top of a book in order to get rid of the air resistance on the feather. It does not matter how heavy or massive an object is. Everything on the planet is going to fall down to the ground at a rate of negative 9.8 meters squared, which means a heavy thing and a light thing are going to reach the ground at the exact same time. As long as we're not worried about massive amounts of air resistance, which we are going to completely ignore in this class, then yes, all heavy things and light things are going to fall to the ground at the same rate, so they would get to the ground at the same time. What does an acceleration of 10 meters per second squared actually mean? Well, it means 10 meters per second. That means that your speed would increase at a rate of 10 meters per second every second that you have that acceleration. So let's assume that you're in your car and your car's speedometer reads in meters per second. So you're at a stoplight, you hit the gas pedal, giving your car an acceleration of 10 meters per second, or 10 meters per second squared. If you do that, you hit the gas pedal, your speedometer after 1 second, 1/1000, the speedometer is going to go up to 10 meters per second. 2/1000, it's gone up a little bit higher. Now it says 20 meters per second. 3/1000, it's up to 30. Every second that your foot hits that gas pedal and gives your car that acceleration, your speedometer goes up by 10. So a 10 meter per second speed increase per every second that you have that acceleration. If I throw something up in the air, what do I know about the velocity and the acceleration while it's on its way up, at the maximum height, and on its way back down? We'll take a look at velocity first. We kind of already talked about that when we were talking about acceleration and velocity being in the same or opposite directions. When I throw something up in the air, I know it's getting slower. And it's getting slower because the acceleration and velocity are in opposite directions. Don't forget that. But we know that it has to be getting slower because, again, if it was going at a constant speed when I throw it up in the air, it would never come back. It would just go on forever. So it has to be slowing down until it reaches the maximum height, and at the very tippy top, it's got to stop going up so it can start coming back down. So the velocity at the highest possible point for just a moment, just an instant, is 0. No velocity at the highest possible point, but then it's going to get faster and faster and faster as it falls back down to you. So that's the velocity through the entire path of something that you throw up in the air. It slows down on its way up, it's 0 at the top, and gets faster and faster and faster on the way back down. What's the acceleration? Well, on the way up, it's negative 9.8 meters per second squared. At the highest point, it's negative 9.8 meters per second squared. And on the way down, it's negative 9.8 meters per second squared. That's because that negative 9.8 meters per second squared is a result of gravity pulling on every object that you might throw up into the air. Well, gravity is always going to be there. It's always going to be the same. So whether you throw it up in the air and it's on its way up, or it's at the top or on its way down, gravity is reaching up and grabbing it and pulling it back down to the ground at all times. And it always pulls it down with the same amount of strength, giving it the same acceleration, negative 9.8 meters per second squared. So what do the displacement and versus time and velocity versus time graphs look like for an object that has a constant velocity? We did a couple of labs on these, so hopefully you remember this stuff. So if you have something that's going at a constant velocity, your displacement versus time graph is going to have a nice straight line that's going to have a constant slope. That's because ultimately my displacement here is going up a particular amount. My displacement goes so far in the same amount of time every time. So what I mean, if I have a velocity of, let's say, 5 meters per second, and it's constant, it does not change, every second I go 5 meters. So my displacement would go up 5 over 1 second, up 5 over 1 second, up 5 over 1 second. And that's what this is showing. In this case, it's just 1. So it goes up 1 meter per 1 second, up 1 meter in 1 second, up 1 meter in 1 second, giving me a nice constant slope, which is the velocity of the object. For the velocity versus time graph, if the velocity doesn't change, it's not accelerating, so it's constant velocity, then the velocity is not getting any higher, and it's not getting any lower, so I get that nice, flat, straight line. Well, what does it look like if the object is accelerating? Well, for displacement versus time graph, you're going to get a parabola. You're going to get a curvy line. The reason for this is, at the beginning, my velocity is really slow. So I'm not going up very far per 1 second over. As you can see, it's a very tiny bit that it's raised up after 1 second of time increase. Well, then after one more second of time increase from 1 to 2, it goes up a little bit more because you're a little bit faster. So maybe you're covering, instead of 1 meter per second, maybe now it's 3 meters per second. So you covered a bit more time during that, or a bit more distance during that 1 second. And then from 2 to 3, it covers even more distance because you got faster. And then from 3 to 4, you're going faster still, so you cover even more distance. And that's why it's getting steeper and steeper and steeper, giving you this parabolic curve on a displacement time graph for an object that's getting faster and faster. On a velocity versus time graph, you are accelerating, which means your velocity is changing. And we only deal with constant acceleration here, meaning the velocity is going to change by the same amount every second. So you can see here, my velocity got bigger by 1 after 1 second, then it got bigger again 1 after another in 1 more second, and then it went up 1 and over 1 second. So you're going to get, just kind of like we had before with the displacement versus time, it's going to look very similar. It's going to be a nice straight line with a constant slope. So those are the answers to your kinematics concept questions. If you have any questions about these, don't hesitate to reach out and we'll talk.